This lecture is brought to you by Megger, a leading manufacturer of electrical test and measurement equipment. I've trusted Megger's equipment for years and have witnessed firsthand their commitment to education and supporting technical schools across the country. For a limited time, Megger is offering my viewers an exclusive discount on their next purchase on products sold through U.S. distributors. Simply visit us.megger.com/bigbadtech for all the details. Good day and welcome to Big Bad Tech. I'm your instructor, Jim Pytel, and today's topic of discussion is center tapped and distribution transformers. Our objective is to take a closer look at center tapped transformers and discuss the role of distribution transformers in split phase or single phase three-wire systems. Recall in the transformer connection diagrams lecture, available at the Big Bad Tech channel, we introduced phase dot notation, where the terminals identified with the phase dots simultaneously achieve the same polarity. For example, consider a 1-to-1 isolation transformer with a 240 volt, 200 amp rated primary and secondary windings. This transformer will be capable of transferring 240 times 200 or 48 kilovolt amperes of power without physical or electrical contact. Isolation between the primary and secondary windings allow a degree of flexibility in the system, and that the primary side could be grounded and the secondary side could be ungrounded or floating, or vice versa. For now, let's assume both sides are floating without reference to ground. If terminals H1 and L1 are identified with a phase dot, this means when H1 peaks positively, so does L1. Similarly, when H1 valleys negatively, so does L1. Long story short, H1 to H2 is perfectly in phase with L1 to L2. Given a 1-to-1 turns ratio, secondary winding L1 experiences 240 volts RMS. Any load between terminals L1 and L2 would experience 240 volts. If we were to add a tap on the secondary winding called N exactly in the center, such that an equal number of turns appear between both halves of the secondary, we could think of this as two secondary windings with a phase dot at L1 and at N. Keep in mind this system is presently floating with no reference to ground. When H1 to H2 peaks positively, a voltmeter placed positive to negative L1 to N would also peak positively, as would a voltmeter placed positive to negative N to L2. Similarly, when H1 to H2 valleys negatively, a voltmeter placed positive to negative L1 to N would valley negatively, as would a voltmeter placed positive to negative N to L2. Again, given this system is presently floating with no reference to ground, this would result in three possible outputs: L1 to L2 with 240 volt differential, L1 to N at 120 volts, and N to L2 at 120 volts, all in phase with one another. This should be a review of the contents we previously discussed in the transformer connection diagrams lecture. Let us now consider these two subtle modifications to this system. 1. Central tap N, henceforth called neutral, is ground referenced. 2. Both voltmeters use the neutral connection as the reference. Voltmeter 1 measures L1 to neutral, positive to negative. Voltmeter 2 measures L2 to neutral, positive to negative. Importantly, ground referencing the center tap does not change the location of the phase dots. When H1 is higher or more positive than H2, L1 is higher or more positive than N, and N is higher or more positive than L2. This also means L2 is lower or more negative than N. I say again, when N is higher or more positive than L2, this simultaneously implies L2 is lower or more negative than N. When N is ground referenced and voltmeter 2 uses the neutral connection as the reference, it can be said when H1 to H2 and L1 to L2 peak positively, L1 also peaks positively and L2 valleys negatively. With ground as the established reference, L1 and L2 are equal in magnitude yet perfectly out of phase with one another. I say again, with ground as the established reference, L1 to neutral and L2 to neutral are equal in magnitude, yet perfectly out of phase with one another. If we were to express these voltages as phasor equivalents, H1 to H2 would be 240 volts at an angle of 0 degrees, L1 to neutral would be 120 volts at an angle of 0 degrees, and L2 to neutral would be 120 volts at either positive or negative 180 degrees. L1 to L2 would be 120 at an angle of 0 degrees, minus 120 at an angle of 180 degrees, or 240 volts at an angle of 0 degrees. This is what is known as a split phase or single phase three-wire system, where the three wires in question are L1, L2, and neutral. This is a common type of residential power distribution system in the United States. 240 volts comes into a distribution transformer and it's split into two 120 volt phases, L1 to neutral and L2 to neutral equal in magnitude yet perfectly out of phase with one another. This type of system additionally allows 240 volts between L1 and L2 for larger electrical loads like water heaters, ovens, dryers, car chargers, and outlets for equipment like welders. Let's explore the operation of a split-phase system by way of an illustrated example. You note I've included a mechanically interlocked 200 amp circuit breaker on both L1 and L2. You can think of this as a master switch that selectively enables or disables all loads. Anytime current is in excess of 200 amperes, the circuit breaker opens up and disables the complete system. Customarily, an attempt is made at balancing loads in a split-phase system such that L1 and L2 experience the same amount of power, or nearly so. Consider the lighting in one section of a house modeled as a purely resistive 40 ohm load on L1, and lighting in another section of the same house also modeled as a purely resistive 40 ohm load on L2. Both these loads are serviced by 10 amp circuit breakers on the hot or high side of the given phase. An application of Ohm's law solving for current demonstrates the first lighting load draws 3 amps at an angle of 0 degrees. A subsequent application of the AC power formula demonstrates the first lighting load consumes 360 volt amperes of apparent power, of which 360 watts is directed towards real power and 0 VARs is directed towards a reactive interchange. Similarly, an application of Ohm's law demonstrates the second lighting load draws 3 amps at an angle of 180 degrees, equal in magnitude, yet perfectly out of phase with the lighting load on L1. A subsequent application of the AC power formula demonstrates the second lighting load also consumes 360 volt amperes of apparent power, of which 360 watts is directed towards real power and 0 VARs is directed towards a reactive interchange. In totality, this system is supplying 360 plus 360, or 720 volt amperes. If we were to assume this transformer is 100% efficient, we can say that the primary must also provide 720 volt amperes of apparent power, all of which is directed towards real power. An algebraic manipulation of the AC power formula, solving for current, demonstrates the 240 volt primary draws 3 amps at an angle of 0 degrees. With the system in the presently balanced condition, you will note that the current drawn by each load is equal in magnitude, yet perfectly out of phase with one another. It's helpful to remind ourselves that phasors are merely shorthand representations of sinusoidally oscillating conditions. At a given moment when 3 amps of current enters lighting load 1, 3 amps of current happens to be leaving lighting load 2. The return path afforded by the neutral line is the current in lighting 1 plus the current in lighting 2. Given current in the lighting loads are equal in magnitude and out of phase with one another, current in the neutral line, while in the balanced condition, is 0 amps. This is true only in the balanced condition. Let's say a heater modeled as a 30 ohm purely resistive load and protected by a 20 amp circuit breaker on L1 turns on. The presence of the heater in no way, shape, or form affects the two lighting loads. They continue to draw 3 amps of current out of phase with one another, and each consumes 360 watts of power. An application of Ohm's law demonstrates the heater draws 4 amps at an angle of 0 degrees from L1. An application of the AC power formula demonstrates the heater consumes 480 volt amperes of apparent power, of which 480 watts is directed towards real power and 0 VARs is directed towards a reactive interchange. In totality, this system is now supplying 360 plus 480, or 1,200 volt amperes. If we were to assume this transformer is 100% efficient, we can say the primary must also supply 1.2 kilovolt amperes of apparent power, all of which is directed towards real power. An algebraic manipulation of the AC power formula, solving for current, demonstrates the 240 volt primary draws 5 amps at an angle of 0 degrees. With the system in the presently unbalanced condition, you will note that current drawn from L1 and L2 are no longer equal in magnitude with one another. L1 provides 3 amps at an angle of 0 degrees to lighting load 1, plus 4 amps at an angle of 0 degrees to the heater, or a total of 7 amps at an angle of 0 degrees. Whereas L2 provides only 3 amps at an angle of 180 degrees to lighting load 2. The return path afforded by the neutral line carries current to the first lighting load, plus current to the heater, plus current to the second lighting load. Substituting in our given values demonstrates current in the neutral line is 4 amps at an angle of 0 degrees, i.e. the degree of imbalance between that drawn from phases L1 and L2. Note the state of balance of a distribution transformer is also affected by the inductive or capacitive nature of loads on given phases.